Alright, this is a follow-up video to solving quadratics. I said I wanted to make some that had some, we'll call them nasty examples. So where the easy way of solving doesn't work out, we have to try something else. So starting off with one that's in standard form, like this one, y equals 2x squared minus 5x plus 7. Remember that when you're trying to solve for the x-intercepts, that's when y is equal to 0. You want to try to factor this. So we could try 2x and x, and 7 and 1. And if I had a negative 7x and a positive 1, I could get my negative 5x in the middle. The problem is that negative 7 times positive 1 doesn't give me a positive 7. So in this case, it looks like this quadratic is not going to factor. So if it doesn't factor, well, you still have options to find the x-intercepts, but something that you know about them is they're not going to be pretty numbers. So you have to use the quadratic formula. Fun times. It should happen sometimes. So that's x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Quadratic formula. So here, notice that b is a negative 5. So we plug it in and get x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And we can start working that out and see what happens. 5 plus or minus the square root of 25 minus 4 times 2 is 8 times 7 is 56 all over 4. And notice that 25 minus 56, we're going to end up getting a negative number here inside of the square root, which is bad because, as you know, you can't take the square root of a negative number, at least not when you're looking at real solutions or things you can graph. So what this tells us is that our graph has no x-intercepts. And technically, all you really have to look at is the discriminant. If you want to figure out how many x-intercepts you have, the discriminant is the part under the square root, the b squared minus 4ac. And if that comes out as negative, well, you know you can't take the square root of a negative number. So if the discriminant is a negative number, then you're not going to get any solutions. If it's equal to 0, you'll get one solution. And if it's positive, well, you'll get plus or minus a positive number here, so you'll get 2 solutions. So the discriminant can save you some time. It's a little bit less stuff to write down. And if it comes out to be 0 or positive, well, then you can go ahead and fill in what b squared minus 4ac comes out to be. But again, we don't get any x-intercepts in this graph because we're going to get the square root of a negative. So we can jump into finding the y-intercept, which if you're in standard form, it's always easy. There's no nasty number solution there that's going to trip you up. So you just plug in 0 for x. So you get 2 times 0 squared minus 5 times 0 plus 7, which would just be 7. So we do have a y-intercept. Your graph, if it's a parabola, will always have a y-intercept that you can find, but we didn't have any x-intercepts. We tried to find them using the quadratic formula, but they just didn't exist. Alright, here's an example that's in vertex form. Again, start off solving it about the same way. So we would add 7 to both sides, and then divide by negative 2, and then take the square root. And notice again, we can't take the square root of a negative number, so we found out a little faster in vertex form that we don't have any x-intercepts. Okay, so there just aren't any defined because you can't take the square root of a negative. We can find the y-intercept though. So y equals negative 2, 0 plus 3 squared minus 7. So 3 squared would be 9. And that'd be negative 18 minus 7, which is negative 25. Alright, so there's 2 examples of what can happen where your equation may not have any x-intercepts and how to recognize that. So when you run into that square root of a negative problem. But the y-intercept, you'll always have one, and it's usually the same difficulty to find it no matter what. Alright, let's look at one more example here. Actually, 2 more examples. I'll do one of each. So, let's try to think of one that is going to have x-intercepts. 3x squared minus 4x minus 10. 5 and 2. Just checking to make sure it won't factor. I think that one's good. And y equals 2 x minus 3 squared minus 5. Okay, so both of these are going to have x-intercepts. Again, they're not fun to find, but they do have them, so let's see what we can do. So start off, you always want to start off trying to factor it. In this case, I already know that this is not going to factor, but I'll prove it to you. So 10 could only be 2 and 5, 5 and 2, 10 and 1, or 1 and 10. Those are the only possibilities. So 3 times 5 is 15. Plus or minus 2 would only be 17 or 13, not negative 4. That doesn't work. Alright, 3 times 2 is 6. 5 times 1 is 5. 6 and 5 could be 11 or 1. Again, those are not negative 4, so that doesn't work. 3 times 1 is 3. 10 times 1 is 10. That could be 13 or 7. Again, not negative 4. And 3 times 10 is 30. Plus or minus 1 could be 29 or 31, but not negative 4. So no combination here of numbers can make this factor. So let's go ahead and check and look at the discriminant first. B squared minus 4ac. Just to prove to you that this does have solutions. So minus b squared, or sorry, positive b squared, but it is negative. So minus 4 times 3 times negative 10. Just plugging in a, b, and c. So we'd get 16 minus 12 times negative 10. So 16 minus 120. If it's a negative 20, that'd be 16 plus 120, which is 136. Okay, so since this came out to be a positive, that means that our graph is going to have 2 solutions or 2 x-intercepts at actual points on the x-axis, which is cool. So plugging this into the quadratic formula, we already know that b squared minus 4ac is 136. We just found that out. So x equals minus b plus or minus the square root of the discriminant all over 2a, which would be minus b plus or minus the square root of 136 all over 2 times a, which is 3. So we get 4 plus or minus the square root of 136 over 6. Okay, so that's where your x-intercepts are. And usually finding them is enough. However, it's not really useful to you to find them if you can't graph those solutions. So what we can do at this step is we can approximate. So we know that, for example, the square root of 100 would be 10. The square root of 121 is 11. The square root of 144 is 12. So the square root of 136 would fall somewhere between these two. It's in other words, it's about 11 and a half, roughly. It won't be exactly 11 and a half, but 11 and a half is a good approximation. So from here on out, I'm not going to write equal to anymore. I'm going to write approximately equals. Because because I'm just trying to approximate so I can figure out where to graph these things at. So I have two solutions here. We'd have 4 plus 11.5 over 6, which would be 15.5 over 6, which is pretty close to 16 over 6, which is again pretty close to about 2.5. So one of my x-intercepts is somewhere between 2 and 3. Okay, so that's good, kind of cool to know. The other one would be at 4 minus 11.5 over 6, which would be, well, 4 minus 11.5 is negative 7.5 over 6, which is, just barely bigger than negative 1. We'll call it negative 1.5, but really it's just going to mean that we have an x-intercept somewhere between negative 1 and negative 2. So here's just the process for what I do if I want to figure out on my graph where my x-intercepts are. I know I have one between 2 and 3, and I have one between negative 1 and negative 2. So I can plot some points there just to give myself a rough idea of where my x-intercepts are. Again, this is a nasty solution. That's what I would call it. So, and then finding the y-intercept again is super easy. It would just be at 0. And really we can just look at the last number, because if you plug in zeros here, those are both going to disappear. So y would equal, or the y-intercept would be at 0, negative 10. So somewhere way down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Way down there. If this were drawn to scale, it would be further down. We'd have our y-intercept. And then looking at the way this is laid out, I could also figure out that my my vertex would be closer. It'd be somewhere on the positive side, since this isn't exactly in the middle of these 2 points. My vertex has to be exactly in the middle of those 2 points, so it would have to be somewhere around here. If you look back up at your equation here, I can actually figure out it would be at x equals 4 over 6, which would be 2/3. So just a little bit of cool stuff you can do, even though you have nasty solutions. You can still approximate and find some neat stuff, like your axis of symmetry, and you can approximate your x-intercepts. Alright, so what if it's in vertex form? Well, you start off the same way. You would add 5 to both sides. You would divide by 2. You would take the square root of that. You would add 3 to that. X would equal 3 plus or minus the square root of 5/2, which is like 3 plus or minus the square root of 2.5, which is like 3 plus or minus, here I'm starting to approximate. I guess this is still technically true. But the square root of 2.5 is something that's a little over 1. So one of my points would be at 3 plus 1.5, and one of them would be at 3 minus 1.5. In other words, I'd have one about approximately 4.5, 0, and one at approximately 1.5, 0. So we can approximate to find out where your x-intercepts are, about. And then your y-intercept, again, there's no real way to make it difficult to find. You're just plugging in 0 for x and trying to solve for y. So you'd get 2 times 9 minus 5, which would be 13. So your y-intercept is at 0, 13. Okay. So there's, a rough walkthrough of what to do when you get nasty stuff happening with your quadratics. I really hope that you don't have any examples that are as bad as some of these. But feel free to pause the video, rewind, watch it over and over again until it makes sense. I've talked about some really cool stuff like how to approximate to give you a better idea when you're graphing where your x-intercepts are when they come up with nasty numbers. So feel free to rewatch this if you want. If you have any questions, feel free to leave a comment below. Otherwise, good luck.